Yeah, just go like this, not this. Exactly. Yeah, that's all right. Good morning, everyone. So we're going to pick up where we left off yesterday, and I think start with Thompson sampling and some more reinforcement learning. This is being streamed over Zoom, so you can access it on your laptop. I don't know how loud the speaker is going to be, so please be mindful about volume level and things like that while we're listening to Ari's presentation. I believe she should be able to hear us, and we should hopefully be able to hear her. So, yeah.
Are you still able to hear me?
Yes.
Perfect. Oh my gosh. So it turns out that I was indeed exposed to COVID. My spouse tested positive yesterday evening after we returned. So I think it's just best to be safe for everybody. That I, just do this remotely, and I think it's still fine mostly, but it's still unfortunate. So yeah, it's kind of sad that I will not be able to see you guys, the folks who signed up for lunch. But hopefully we have other opportunities to meet, and we can make up for that at some point. In any case, so I mean, since most of this lecture was written on some of these slides, I guess we could just go over them and pretend there was like a person walking around over there that looked like me or something. But anyway, so yeah, let's pick up where we were yesterday. I'll do a little review to make sure that we remember and refresh our minds about where we were yesterday, and then we're going to get into a little bit Thompson sampling and see how that looks like from a very different perspective of how to make decisions, and why that may be sort of like more intuitive from a more statistical Bayesian sort of point of view. And then depending on time, I'll get into a little bit of how reinforcement learning looks like, and at least one application where that process has been applied in my research, and how you could take it further and start making good real-time decisions for getting physics related information. So let's hope we get there, but we'll iterate as we like. So yeah, I do hear a little feedback, Brian. It's not totally bothersome. I guess it's important because I don't it's probably not okay. That was muted. Okay. I think Brian has the control somewhere. He's the guru god who's been sitting. Okay. So so here's where we were. Let's see if my marker will work. Okay, there we go. Okay. So yesterday we started talking about how we have this new paradigm of a set of tools that we can use to make decisions in the presence of incomplete information. And we talked about how this type of domain is different from traditional supervised and unsupervised learning in multiple aspects, in that we spend time thinking about whether we want to act on our best belief or acquire more information, with the goal that despite that uncertainty, at the end of the day, you do well, you make good decisions, and you get good rewards. We talked a bit about generalization, although in this case, we are not doing generalization in that the agent is learning in its own environment. So some of the examples that you've seen, Greedy, eGreedy, and UCB are all learning online. So online just means that it's learning as it's gathering experience. And it does not generalize to, so if you give it another MDP, which is a different NDP with a similar formulation, but not exactly the same parameters, it will not be able to make good decisions. We also talked a bit about, sorry about that. We also talked a little bit about delayed consequences at the beginning, but we didn't touch on this later because at least the type of Markov decision processes we were talking about, we get rewards immediately. But we did mention at the start that this is not always the case. There are situations in which you make decisions now, but you don't get information until much later as to how well you did. This is particularly important because in many cases, when we collect data in astronomy, we don't get immediate feedback, either because data reduction takes time or because if you're thinking about things like transients, which I'm very interested in, we usually get incomplete information when we start, but we want to do inference with the complete data. So even though we collect data today, the inference on sort of the entire data set would only happen once we have gone through all the episode and have collected all the data. So it's relevant, although it's not, we didn't talk about it, but we may get to some of that depending on how fast we go. And I just wanted to clarify in this picture over here that I showed last time, even though reinforcement learning is a small one, I just meant in terms of like how, so this is really in terms of how much the applications are. So if you think about applications, reinforcement learning is not small. I don't want to give this illusion that it's small in terms of methodology. It's actually quite extensive. But in terms of like how people are using it compared to some of the other approaches, it's smaller. And we talked a bit about how we have this classical setup of an agent that interacts with an environment and is presented with information about the world, at any given time, denoted as T, and takes actions towards the environment that is received by the environment, and all you get back from the environment is the next state and a reward associated with how well it did the last time. And action. And then we talked a little bit about, describing all these parameters, state, action, reward, policy, which are usually important for defining Markov decision processes and and setting up reinforcement learning more generally. So this was the introduction. I should mention that yesterday I spent a little bit of time rearranging these slides. So as you can see, sort of like I grouped them in sort of a more meaningful fashion. However, the good thing about OneNote is that you can always go back in page history. And if you're a very visual learner, this may bother you. So you can always go back to see how exactly it was written. Well, we were discussing this in class, but as I'm going through this, you will see that it should make more intuitive sense. So it's been rearranged a little bit, so don't be surprised. I'm hoping that's helpful. But if it's not, you can always access the history. So we were talking about, just grab a little water. So we were talking about a very simple domain called multi-arm bandits, where you're always given a set of M actions or M arms that you can exercise or move at any given point of time. And each of these arms is associated with an unknown probability distribution. Oh my gosh, I make so many typos when I write reward. It's associated with an unknown probability distribution. Hold on one second. I need to fix my screen on my computer so it's not in my way. Okay. Unknown probability distribution that you don't know, but it's conditioned on the arm that you pull. And we talked about how specifically this could look like for astronomy. We made it a little more concrete. But the idea is that you at every time step, you select one action from all the actions, so from all the M arms, and you get a sample, a single sample from the reward distribution at each time step from the arm that you pull. And as you interact in this Markov decision process environment, your goal is to maximize your cumulative rewards. Essentially, we characterize it like that. And we went through a bunch of definitions. We thought this was going to be useful. Specifically, we are interested in this notion of regret, which is a theoretical tool for studying algorithms and how algorithms perform. And we were thinking about like a little bit more about how we could quantify this well. So we concretely defined a situation where we have three different arms that correspond to groups of objects that each is associated with an as yet unknown probability distribution of hosting planets. We wanted to see if we could spend some very expensive telescope time to get high resolution light curves. And once we did, we get something like this. And if we see a planet in that light curve, we always can say, yes, we see it, and no, if we don't. This type of a reward distribution is known as a Bernoulli. We talked about that. Bernoulli is useful because there are many situations in which you have Bernoulli rewards in the real world. In the healthcare setting, you can go and take a test. You are positive or negative. And I've seen this applied in the industry in terms of like ad clicking. So if you have a group of people that you're going to test for A/B testing, you have a particular design choice, and you want to see if A or B is more successful. And the idea is that A and B both have unknown underlying probability distributions, and you want to present A and B to users such that you sort of make sure that you get the maximum amount of clicks. So Bernoulli is a very intuitive reward. We're going to fixate on this, but the examples that I'm going to give you and the ones I've given you are not constrained to Bernoulli. So especially UCB makes absolutely no assumptions on the underlying reward distribution. Thompson sampling does, but there are changes that you can make to consider different reward distributions. And the thing I mentioned is that this is a very simplified domain because all our pulls are IID, which means a single pull does not, a single decision now does not affect a decision that you make later, which we don't always have the liberty to do. In reinforcement learning, we actually get rid of that and we try to make good decisions overall. We basically specified that, in our toy example, we have Bernoulli rewards with these parameters, and we don't know them. So we want to make good decisions. And then we went through and we talked about a very simple algorithm that one of your colleagues suggested, and I guess you would if you didn't know anything about reinforcement learning. And what you could do is essentially just explore and get data on the world. So you would get an empirical estimate of how good each arm is, which is just an empirical average. And then you can just get the action that has given you the best reward so far, and you can select that action and keep making decisions. And we demonstrated how essentially, even though you can be in practice very good, especially if the rewards are quite separated, as we have in this case, in practice, you can end up with very bad performance if you get unlucky. And it's not optimal. So we showed how situations like this can lead to linear regret. We didn't get to code this last time, but intuitively you can imagine how at least some fraction of the time in any initialization, you could end up with a sample that makes one distribution accidentally or unluckily look better than the other one. And you can just be like, okay, now this is great, I'm going to stick with this, and that wouldn't be a good choice. So we wanted to do better. So we thought about, oh, hey, what about we sort of make sure that we don't become so greedy and we still do something random. And so what we said was, hey, so instead of like doing a greedy all the time, let's do greedy some part of the time. And we're going to still spend some fraction of the time being exploring. We walked through an example of how still this could have linear regret. And the idea is that every time you have linear regret, you are not learning, and we want to still start making good decisions. So we wanted to talk about some of these more advanced algorithms, and yesterday we introduced UCB. In UCB, we have this notion of optimism under uncertainty, which is a very powerful concept. And we want to essentially choose actions that may give us good results. So we just want to take the upper limit of the expected reward distribution that we have a running estimate for, as we have in the previous case. We keep running estimate, but in this case we add a constant factor, and we assume that's what we're going to get, and we're gonna exploit on that, and we update as soon as we get any information. And we showed why this is a good thing to do. Essentially, there's a very elegant theoretical proof that this is a good idea. Essentially, yeah, so we have this, instead of like selecting actions with the best Q value, you estimate the action with the best upper confidence bound, which is this constant factor slapped on top of the running estimate. And we said this is powerful because UCB makes no assumption about the reward shape. And this has sublinear regret. You can show this, which means you actually learn iteratively as you start making decision and make updates. So this is your learning. And we demonstrated with an algorithm essentially that this is making intelligent decisions of how to explore the space further and continuously learn. And you can show if you complete, well, if you follow either the theoretical proof and you believe it, well, you believe it if it's a proof, but or if you code it up and you see the results, you'll actually see that this is a good thing to do. And so far so good. And we basically spent some time discussing a pseudocode, which we're not going to pursue. So now we're going to think about a little. Oh, actually, let me pause and see if we have questions so far before we move on to Thompson sampling a bit. All right. I think there's one question I see. Maybe. Or if you want, you can chat, write it in the chat as well, if that's easier for everybody. So Jordan says, hey, Ari, even with different methods, are there any cases where you'd want to use greedy versus one of the better ones, even with different methods? So are you asking whether greedy is a good, okay, like, is it computational power? Is it just, no, so it's, so greedy can be bad in some cases. So you can actually end up with really poor performance. So it's, so I think computationally speaking, at least the algorithms that we are presenting are pretty simple. You can code it up and they're going to have very little additional overhead. It's thus that you're going to accumulate a lot more regret in expectation with greedy or e-greedy versus UCB and Thompson sampling, both of which exhibit sublinear regret asymptotically as you learn more and more. So it's, you'd want to go with UCB and Thompson sampling, which we're going to talk about in a second, because you want to start making good decisions and learn from your data. So you can still implement greedy. It's just that, you know, it's probably not going to be the best choice for allocating resources. So you would, and I mentioned the A/B testing, for example. Most of the A/B testing that you're actually seeing that you interact with online usually involve Thompson sampling. So people don't really use greedy or e-greedy or random. There are a bunch of other strategies. You can always be random some fraction of the time. Like, you know, in e-greedy, you can be E 100% of the time, which is probably what you would naively do. You can do grid sampling. There are other stuff, but all of these other strategies are associated with linear regret. So you just want to do better and accumulate less regret. And it's just, it's a good, it's an easy enough implementation that once you get it, it makes sense that you want to do that. Does that answer your question? Okay, perfect. Thank you. All right, so we're gonna move ahead. We're gonna talk about Thompson sampling. And I was actually really annoyed yesterday that we couldn't do it in person, because Thompson sampling is not only very effective, it doesn't even not only leverages some of the statistical inference stuff that you've talked about in the school before, but it's also really fun. It's also empirically much better, and you'll see why in a second. But it's I like it much more than UCB, even though UCB is pretty powerful and we can use it for a wide set of reward distributions. In general, you know, you may want to use Thompson sampling. So let's talk about it. So we're going to talk about Thompson sampling today. Thompson sampling. And the idea in this case, as opposed to the last time, is that we don't, so in UCB, we were thinking about optimism under uncertainty. Now we want to think about, we were sort of a little Bayesian about the world. So we're going to think about Bayesian bandits a little bit. Oh my gosh, give me 1 second. Bayesian. And this Bayesian perspective is useful in some sense. So there's obviously a little bit of a philosophical disagreement between folks whether, you know, we use a frequentist or a Bayesian point of view of the world. We're not going to talk about this, but I think some people appreciate having sort of this notion of like, having a prior that you maintain about the world and you update as you receive more information. So Bayesian bandits essentially has the Markov decision process in mind, where you still have your agent that interacts with your environment in an iterative fashion. And this updates regularly. And the idea is that the agent maintains a prior belief of the environment that they get to update as they start receiving more and more rewards from the environment. And the hope is that based on the reward history, you make good decisions and your actions are optimal and give good rewards and expectation given the history. So essentially, the idea is that on every single interaction, the key idea is that you want to compute a posterior distribution of rewards that you could get from each arm. So you may start with a prior, but then you update with a posterior. So we're going to be a little more Bayesian about this. And so, classically, if you can write this, let me just write it in the formula version that we're going to keep using. So we have, let's talk about this a little more carefully. It'll take a little bit of time to absorb it, and I'm happy to like iterate through this as much until people totally get it. So let me write this down first. So this is the likelihood. This is your prior that you're maintaining. And your normalization, evidence of data. Okay. So essentially, if you've talked about statistical inference in this in the context of this school, this first part is your posterior. It tells you how likely are your parameters phi that describe your the belief of some set of parameters. This is the distribution of parameters that you're maintaining given the data that you see, and R in our case is rewards. This part here is the likelihood, which is saying how likely will you see a certain reward given the parameters phi. And this one is your prior. Okay, so what we want to do here is that we're going to be a little Bayesian about the world, as we were saying. So we're going to say that we will assume that phi of I is a parameter that describes the probability distribution of the rewards. So let me write this. I'll be a little concrete about this because I think otherwise we can get lost in the details. It's a parameter that describes So if you think about the previous case where we had the situation where we had a Bernoulli reward with a parameter P, and these parameters were 0.7, 0.95, 0.9, and 0.1 for each of the arms that we were considering, arm 1, arm 2, arm 3. What we now want to do is that we want to say that this parameter P is, we maintain a prior belief on this. So we're going to say that this, the phi that we have is maintaining a, is the prior on, we have a prior called phi that is a distribution of the parameters that we can get for that arm. And of course, the truth is that it's 0.95, but we don't know what it is. So we may start with a flat distribution. And what we want to do is that we want to update this as we start getting rewards on what the true parameter P of I is. So that's our prior. So that it would make sense that this would be something that you want to do because you want to update exactly what you want to learn what these parameters are through your learning process. So we're going to introduce, yeah, so let me just clarify. So what this is this one is, oh no, let me say this better. So Ri of 1 is the reward that you get, reward at time step I from pulling arm 1. Oh, I think I mixed that up. Let's okay. I think it's at time step 1 from pulling arm I. So phi of I is the prior that you have on arm I. On any given time step that you pull that arm, you will get a reward for that arm, and you will update your prior that will eventually start telling you more and more about the parameter that describes the true arm. So that's the idea. So how are we going to do this? So let me introduce as a quick aside what these mathematical quantities are called conjugates. So this is an aside, it's important. So how many of you have heard about conjugates in a different context? Maybe conjugates come up every now and then in statistics. It's a useful choice. So conjugates are essentially just saying that it's any mathematical function for which your prior and posterior represent parametric forms are the same. They will be conjugates. So let me just write that down. So if your parametric representation of prior and posterior is the same, they're conjugates. Okay. And so basically what I will note here, and I think this is relevant to us because we're thinking about Bernoulli rewards, that the beta distribution, and we're going to talk about the beta distribution. So the beta distribution is a conjugate for Bernoulli. So what this means essentially, so let me actually use a different color ink so that it becomes a little clearer. So what I'm saying essentially is that we're going to think about these distribution, we're going to think about these now different types of functions, conjugates, that is going to help us. And the idea is that if we start with a prior that is of a certain parametric form, and we end up via the Bayesian process in the same posterior form, then the likelihood, so let's say this, for example, then these, for example, this would be a conjugate. This would be a conjugate for the parametric choice that you're making. So say, for example, that if I say that my prior is a beta distribution, this is a beta distribution, and the conjugate, like I said, the beta distribution is a conjugate for Bernoulli, the reward, the likelihood function is actually Bernoulli. We're going to see an example of this in a second. I think it'll become much clearer how this is. But the idea is that essentially the reward, so this one obviously is something that we have specified before. We know that this is Bernoulli, right? We are talking about Bernoulli rewards. And as long as they are conjugates, the beta is a conjugate for Bernoulli, you can actually use this sort of an update in a more useful fashion. So let me say another quick thing here about describing the Bernoulli distribution. On the beta distribution a little bit better. So the beta distribution, which looks like this, the beta distribution is the following. You don't really need this form entirely, but I'm going to write this down for now just so that everybody is clear. It's described by a few parameters, and really we only care about two, which is alpha and beta, and I'm going to show you just what this is in a second. And this is the gamma function. We don't really need the full expression, but I'm going to write this down for completeness. Alpha and beta. So let's we're gonna be a little more concrete about this as we go forward, and things will become a lot more clearer. And if you bear with me and see how this works a little bit. So the good thing about having conjugates that are representing your updates on your reward is that if you have a conjugate family, that you've selected a conjugate family, the update on a posterior, so the updates on your posteriors is in closed form. So you can just do the following, is in closed form. So you can just add +1. So you can do the following. If you receive a reward of +1, so if you receive a reward of +1, your posterior gets updated. Posterior will now be a beta function with a distribution alpha +1, beta. If you get a reward of 0, your posterior will get updated to this parameter. So let's see exactly how concretely this made work. If this seems a little, I think it'll become a lot more clearer when we go through a specific example. So let's see what the algorithm for Thompson sampling might be. Thompson sampling. So what we do, as we did before, and we'll do this before, we'll spend some time initializing. So we'll just pull all the arms, just a little bit, initialize over all arms. Initialize, I'm sorry, with pulls. Okay. Actually, let's just say that's not, let's say the actual updates take place here. Okay. So now we're going to maintain a prior. So we're going to start with a prior distribution over each arm. So we're going to start with an uninformative prior distribution over each arm A. And this is going to be your variable phi. I'm going to make sure that I keep the same notation here. Over the reward distribution, over the parameters that describe the reward distribution of the underlying arm. So there's like a little bit of an a little bit of like a two-layer wrapper that's happening. So you have a prior that describes the parameter, the distribution of parameters that then describe a distribution of the rewards that you're going to get. That's important. And then we're going to do the following. We're going to loop. So this is the algorithm. We're going to loop. And for each arm A, we will sample a reward from the posterior. Posterior. Okay. So, and then what you're going to do is then you're going to compute. I'm just going to write this down, and then I'll go through this step by step in an example and it'll become more clear. So then you're going to compute the action value function, which is essentially just saying, which is your Q, which is your empirical average. You're going to compute the action value function, which is the running estimate. And this is going to be the expected reward for that, for the particular, the reward distribution that you're going to sample. And this is just going to be the mean parameter for the Bernoulli distribution. Bernoulli. And then it's easy, because then you just take the action with the largest reward, arg max, A belongs to A, Q of A. And you're going to observe reward. Observe reward RA. And then you're going to update your posterior according to this. And we're going to see how this works in a second, very concretely, and things will become very, very clear. Hopefully it will. I mean, at least it did for me when I first saw this. Okay, then you're gonna update your post here. This is again gonna be phi RFA. Okay, so let's make this a little more concrete with the example that we've been using so far. So we have 3 arms. We have three groups, right? 1, 2, and 3. 2 and 3, each with parameters theta1, theta2, and theta3 that we don't know what these are, right? So here we're going to maintain a prior. We're going to maintain a prior over these parameters. So phi is over theta, essentially. So phi is over theta. So here we have, the truth is that these are 9.95, 0.9, 0.1. But what we're going to say is that we're going to maintain a prior, and we're going to say we don't know anything what this is. So let's imagine our prior phi over theta. The truth is that it's actually here, right? It's 0.95. But we're going to say we don't know. Initially, we are naive about the world. So we're going to say all values of theta are equally likely. That's what we're going to start with. Okay. And essentially, what this is, if you're going to do it this way, and remember, we are using conjugates because we want to make our updates tractable. We want to say that this distribution is a beta 1,1. The beta 1,1 distribution actually looks like this. So we're going to start for all arms. We're going to start with a flat prior. We're going to say, so this is theta 1, this is theta 2. Sorry, this is theta 2, this is theta 3. We're going to say that we're going to start, and this is 1, phi 2, phi 3. Our Thompson sampling is initially going to have no information about what the true parameters are, and we're going to start with no information. Okay, and this flat prior is described as a uniform distribution. Okay, so let's go through a specific example of how this might work. So we're going to follow this algorithm, right? So we have now done this step. We have a prior distribution. We've done step 1. We've done step 1. We have established a prior distribution over each arm. And now we're going to do this step. We're going to loop over this step. And this is actually a little inside. So let's make it a little indented, right? Because we're looping here. And then in this, after maintaining a prior distribution, we're going to pull each arm and sample a reward distribution. So let's say we're going to be a little silly. We're going to say, okay, you know what? We don't know anything about the world. Let's sample. Let's assume. We're going to pretend that our actual world has a sample somewhere here, and somewhere here. So we're going to say, okay, you know what? We don't know anything about the world. Let's assume that we get a sample. We're going to sample of from the prior over the parameters with one set of parameters like 0.3, 0.5, and oops. And what this is essentially saying is that, at this point, you have said that, the true value is right here, like 0.95, 0.9, and 0.1. This is the true value, but we don't know what this is. So we're going to just pretend like it's some value and see what happens. So we're going to sample from the prior distribution, and we're going to come up with like these 3 fake values that are not real. Okay. And then, of course, then we need to go back here. So what we have done is that we have sampled a reward distribution from and here is the posterior, but it's a prior, and because we're doing an update. So we're going to sample a pretend reward distribution that isn't real. And then we're going to, we then have to compute the action value function, which is just the mean value. So the action value function here is just going to be Q of A1 will be 0.3, Q of A2 will be 0.5, Q of A3 will be 0.6, because this is the mean. That's very easy. And then what you say is that you're gonna pick the reward with the highest expected value. And in this case, that's gonna be arm A3, right? These are all pretend, it's fake. None of this is real. It's fine. You know what? So far, so good. That's what the algorithm's asking us to do. So we're gonna select arm A3. It's not a good arm, but it doesn't matter. You will see how immediately you start doing better. So you've selected arm 3. We were like, okay, you know what? We don't know anything about the world. Let's assume that the reward distribution has a parameter 0.3, 0.5, 0.6. According to me, arm 3 is best. All right. So let's get a reward. Let's act on this environment, and we're going to pull that arm. We're going to get a reward. Let's assume we get a reward 0, because this is actually not a good arm, right? So you say your sample said, oh, it's a reward distribution 0.6, but it's actually not a good arm, so you'll get a reward 0. So now what you're going to do is that you're going to use your update rule. So here what you saw is that if you get a reward 0, your prior needs to get updated in the following fashion. So we had here, remember, so this is beta 1.1, right? This is beta 1.1. If you get a reward of 0 on that, you need to update beta, your phi of 3 needs to become beta 1.2. Because we had that update rule, we said the second parameter needs to be incremented by 1. And let's see what that does. So I'm going to mark this here so you can actually see how fast this update is going to happen. So we were here, right? We have no information about the world. By making this single update, here's what's going to happen. By making this simple update, first of all, the first 2 parameters will not change, right? So you're just updating 1. So phi of 1 over theta of 1 remains flat. Phi of 2 over theta of 2 remains flat. However, phi of 3 has now gotten updated to this. And here's what that looks like. Beta 1.2. This is beta 1.2. Let me make that better. This is beta 1.2. This is over parameters 3. This is phi 3. So immediately your prior is telling you that a theta of a lower value. So again, this is 0 and 1, right? So it's telling you a theta of a value 0 is more likely than a theta of value 1. And that's your update, basically. So notice that between this one and that one, you now have more information. That's what the update is. So let's keep going through, and you see how we'll see how this gets more and more updated, okay? So we'll follow the same protocol, right? So we're going to do the same thing. So this is loop step 1. Let's going to call this 1. Let's do it again, right? We're going to do it again. We're going to sample. We're going to sample reward distributions theta 1, 2, and 3 from these updated priors, phi 1, phi 2, phi 3, from these updated priors. And now let's imagine we get, from this sample, we get theta 1 of 0.7, 0.5, and 0.3. Okay. And in this case, of course, like, because you are now sorry, let me just use my my pointer if my computer responds. So here, obviously, since you're skewed, you're more likely to get a theta that's lower. So it's not surprising you get number of 0.3. So we get these. Okay, that's just luck in life. That's what we get. Write this better. Okay. And then according to this before, we need to compute what the Q values are. So again, they're just the means. So Q of A1 is 0.7. Q of A2 is 0.5. Q of A3 is 0.3. Okay. So we need to just now select the arm with the highest expected reward. And that's just going to be right now arm 1. Okay. So we're going to select arm 1. Select A1. We're going to act on the environment. We're going to get a reward 1 because it's a good arm, right? We're going to get a good arm. This is just it. Let's say we get reward 1. So now we need to update our posterior, and we go back to this, right? We have our update rule. So if you get a reward 1, your posterior needs to get updated with 1 being added on to the alpha parameter. So your phi 1 update, your update of phi 1 is going to be equal to a beta of 2.1. So what is our new prior? What is the new posterior? Sorry, not prior. What is the posterior going to be on the parameters that describe the reward distributions in the new case? This is what it's going to look like. So B3 will remain the same. We haven't made any pulls. This one remains the same. It doesn't look very good to us. Okay, so this is phi2, sorry, phi3, phi2, phi1, theta 1, theta 2, theta 3. And a beta 2-1 looks like that. So going from here, you're now here, you've updated. And what this is now telling you is that a theta 1, a parameter for the reward distribution with a high value is more likely. So you're seeing how the prior is getting updated. So let's keep going with this process a little more, and you'll start seeing how we immediately start taking good decisions because of this update. So let's try this step again. So we're going to sample again from these posteriors. So we're going to sample reward distributions. Oh my gosh, I can't write today. Distributions, theta 1, theta 2, theta 3, and we get the following thing. We get, in this case, we get sample theta 1, we get 0.71, we get 0.65, and we get 0.1. All of this makes sense because now our priors are such that we are more likely to sample higher values for theta 1, like any value for theta 2, and smaller values for theta 3. Okay, so in this case, again, we need to compute the Qs. The Q of A1 is going to be 0.71. Q of A2 is going to be 0.65. Q of A3 is going to be 0.1. Okay, so the idea is that you need to select the action with the highest value, and that's going to be A1. So we're going to select A1. And we're going to get a reward 1 because it's a good arm. So now we again need to update our posterior. So we need to update posterior according to our rule, posterior. So we got a reward 1. We go all the way back up. So we get a +1. So we add 1 to alpha. Okay. So now instead of having beta, so we previously had, so this is beta 2-1, right? That's beta 2-1. So we need to update that, and it becomes beta 3-1. Very simple. Just keep track of that. Okay. So now what's that gonna do? How is that reward distribution gonna look like? So let me just make that part of that. So this is this. None of these other arms have changed so far. So this is gonna be that. It's gonna be flat. It's gonna be 5-3, 3-2, 3-1, theta 1, theta 2, theta 3. Because of this, because now we have a beta distribution 3-1, this is what 3-1 looks like. So notice that this is starting to get more and more biased towards start being a theta with a higher and higher value. And so essentially, if again, like, so let's keep going, actually, just one more step here, and then we'll stop and we'll start evaluating all the algorithms together. So we're going to do one more step in this, hold on one second. So we can do one more step here where we sample reward distributions, theta 1, let's say that is 0.85, theta 2 is 0.6, theta 3 is 0.2. And again, your Q of A1 is going to be 0.85. Q of A2 is going to be 0.6. Q of A3 is going to be 0.2. So the idea is that you need to select the one with the maximum Q expected Q value. And we select A1. We get a reward 1. 1. Just to check your understanding at this point, can someone tell me what the updated posterior might be for arm A1 that we have selected? Given this update rule that we have. So we got a reward 1, right? So we got a reward 1. and we need to update our posterior. So what is our new posterior on, what is our new posterior phi1 going to be? Anybody? So let's go back and just make sure that we understand that. So essentially, if we get a reward plus 1, we just need to add 1 to the alpha parameter. So we go from 3 to 4. So that's fairly easy as well. So basically, we have our updated posterior, update posterior. To beta 4-1. And if you again make these distributions, I'm just going to not draw them again for the sake of time. You're going to start being more and more peaked. You're going to be way more peaked that way. So this is how you actually start making updates and getting more and more information. And if you actually implement this in code, the expectation is that as you update, you start actually converging towards the true value. So the hope is that with many updates, Q1 will start, your phi of 1 will start showing you a very peak distribution around 0.95, because that's your true value. So that's what you should have. That's what should happen in Thompson sampling. It's pretty efficient. So let's compare the performance of the algorithms. We had this like way of analyzing all the performance of all the algorithms. So we have the optimal value. Let's just write that down. Optimal action. We have the regret. So here we took A3 first, right? And then we took A1, 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 right? So we go to 0, 1, 1, 1, 1. The optimal action is always the same. A1, 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 A1. And the regret here is going to be, again, the way we described it, as a reminder, that's Q, the value of V star versus the arm that you selected. And the true value, we don't know this, but again, this is a theoretical analysis. We said that this was 0.1, and the actual best value is 0.95. Yeah, 95. So the regret is going to be 0.85. For these, it's going to be 0, 0, 0, 0. So essentially, you can see, and if you really look back and you start comparing to what we had done in any, so let's look at upper confidence bound here, right? We had a similar situation where we had all these arms. So in the case of upper confidence bound, even though once you actually got enough information, it was still trying other arms. Even though it saw a good performance on A1, it was still saying, oh, maybe I'll do well in A2, and I can still try that. So compared to upper confidence bound, where you still like spreading your attention between arms that looked good, especially because that was your strategy, in Thompson sampling, you immediately become aggressive. So this is one of the reasons why Thompson sampling actually works pretty well in practice, and you accumulate initially, even though asymptotically, both UCB and Thompson sampling have similar regret bounds asymptotically. Empirically, you get much better performance because of this sort of like prior that you're maintaining over the parameters. So the last thing I will mention, because before we take a quick break and we come back, is the fact that we've talked about like conjugates in terms of Bernoulli's and beta distributions, right? But of course, we don't always have Bernoulli rewards, and this is fine. There are other implementations of conjugate functions that you can choose. So if your reward distribution, so if your likelihood function is a normal distribution, that's what you expect. The conjugate is also a normal distribution. If it's a multinomial, the conjugate will be a Dirichlet. So there are conjugates you can choose depending on the parametric assumption of the reward distribution that you expect. So you can do this regardless of what you have, but it's useful to demonstrate it for a Bernoulli type reward, because you see that quite often. And I think even in classification cases, yes or no, that's the type of reward distribution you will have. Okay. So I find that, so I'm unfortunately I'm not there, so I'm not able to kind of ascertain if this sort of made sense. I hope it did. It's a beautiful algorithm. It works really well. let me see if people quickly have questions before we break and switch gears to something else entirely. Oh, Brian had mentioned a few minutes ago, hi, not to interrupt, but we should either move to give them an, okay, yeah. Is there any question?
It's unmuted now, so just asking the room. Looks like I'm not seeing any hands. Okay, so oh, there's one hand.
Okay, so if the conjugate gives us the same posteriors, then what's the point of having different distributions that would give you the same answer anyway?
So,
Great.
right. So I did catch that. So I think what was said is that, if the posteriors are the same, how is the update even happening? I think I should have been a little more clear on this. So what we are saying is that the conjugates have a similar parametric representation. So they're coming from the same family of distributions. The exact values don't remain the same. So in this case, for example, you have a beta distribution. You start with parameters alpha and beta, that's 1, 1. And then that's your prior. That is one that's coming from a family of beta distributions. And if your likelihood function is a binomial distribution, you will end up also having a posterior that's a beta distribution, but the parameters will be different. And the update rule, so the way you update it is in closed form, and that's what I was mentioning here. So so you go from having I'm sorry, my slides are a little, so you go from the same parametric family in your prior to the same parametric family in your posterior if your reward distribution is conjugate with the choice of your prior, but the parameters will get updated depending on what's happening in your situation. Does that make sense?
Yes.
Okay, perfect. Yeah. So yeah, this portion is a little more like it takes a little bit to absorb, but essentially if you assume, so I think you start with to clarify, you start with a certain like assumption of what your reward distribution is going to be like, and you choose a conjugate family over which you maintain a prior, and you start with a certain naive assumption usually of what that is, and you have update rules that tell you how to go from that prior to the posterior such that you remain in the same family, and you can keep doing this update, but the parameter itself will get updated in a meaningful fashion given the reward that you see, given the likelihood function or the actual reward, given the reward sample that you get from the reward distribution that is conjugate with your prior, which is here in this case Bernoulli is the, I'm sorry, my screen is being a little delayed. I'll probably restart as you guys are going on break. If you have a reward distribution that's Bernoulli and you're maintaining a prior that's a beta distribution, because they're a conjugate family, your posterior will also end up being a beta distribution with an updated parameter according to this rule. That's it. And yeah. And like I said, there's no reason why we want to stick with Bernoulli's and beta distributions, depending on your domain. If you expect to have a different type of reward family, then there are family choices you can make for those. So yeah.
It looks like there might have been a question or a comment in the chat too.
Oh, I just see that right now. So from the initial arm choice, does that mean we won't really have the opportunity to? That's such an excellent question. So this is actually one of the reasons why, why you may want to choose one arm over the other. So essentially, if you go back down, I'm sorry, my screen's pretty frozen at the moment. Like, give me 1 second to see if I can get this to move. So I want to go down. Hold on 1 second. Actually, let's take a break. I'm gonna because my screen stopped responding for the moment. So let's take a break and come back. I'll try to get my screen to move. And in either case, we'll be using a PowerPoint from now on. But let's take a break. We'll answer Jordan's question after we reconvene in about 5 minutes, maybe.
Yeah, let's do a 5-minute break. So come back at 14 past the hour.
Oh, I'm sorry. Oh, sorry, Brian. I saw the schedule and I thought I'm going up to 10:45. I really apologize. I really got the time wrong. Well, you know what? We'll just wrap up real quick. We don't really. I had some slides to share. I can give you just a quick, punchy overview, like a lightning talk. I never take away from anything from those, but I guess we could just keep it real short. But I just wanted to answer Jordan's question, which is like, okay, if you see this particular example that we've been examining here, it seems that we've now been biased extremely heavily because our prior distribution's been updated through just sampling and luck towards sampling arm one. And does that mean like, now we never get to update any of the other arms? And the idea is that actually in Thomson sampling, you start exploiting much faster than in UCB. So remember yesterday I was in class and I was like, hey, you can have situations when you're updating your algorithm that you can be optimistic, quite optimistic, like overly optimistic. And, you may encounter a bad situation, but your upper confidence bounds tell you, maybe things will be different next time. Okay. And I still, end up making a lot of mistakes. Thomson sampling starts becoming, pretty like aggressive quite early. So in this case, what will happen is that, if you've updated in this fashion and you got these sets of outcomes, yes, you will start focusing more and more on arm one, and it could be a while before you switch to any other arm. But it's because you still have a non-zero probability of having a reward distribution that could. So in this situation, give me 1 second. Oh, I just restarted and everything's messed up. So in this case, as you can see, there is still a non-zero probability distribution over these functions. So it is possible in at least one of the cases, even though you may get a sample from here and a sample from there. And in that case, you will choose arm two. But it may not happen for a while. So you may be stuck with that a little bit. But empirically, I can tell you that this actually works really well. So if you were to think about which distribution you want, there are various reasons why you may want to choose one versus another. But Thomson sampling does really well in practice. So like I said, unfortunately, I don't have enough time with you all today. But I did want to mention that there's actually applications. So because reinforcement learning is a very involved domain, we don't usually get like it's very hard for me to teach you all the intricacies with a very limited time. So it's usually a semester long coursework that you would undertake for something. Adam, did you want to say something?
Sorry, I think there's been a little confusion. We are going to go till 10:45.
Oh, okay. Brian said we are supposed.
Apologies about that. 10:45.
Oh, okay.
Yeah. So.
Okay. Oh, I just see that now. Okay, my mistake. You haven't.
Okay, sorry about that.
Sorry. Okay, all right, no worries. So I do have time. Okay. Yeah, okay, let's do that then. So essentially, yeah. So the idea is that at least I wanted to give you one example where we have applied some of these types of techniques to solving real problems in astronomy. And as I was mentioning, that reinforcement learning is a pretty broad domain, and it's very hard for me to teach all the little nuances in even a few hours that we have. And you can see it can get pretty complicated very fast, and the full reinforcement learning domain is pretty involved. But should you get there are types of problems that you can solve, and some of which, the principles of which I can tell you and make it more concrete as to what types of opportunities are available with techniques of this type. So essentially, whenever you are faced with the problem of making decisions with limited resources, and making them in the presence of incomplete information, this is where you may want to use reinforcement learning. These are also useful when you are constrained to make decisions very fast and in real time. So I'm particularly interested in the domain. Let's see if I can get my screens to advance. Perfect. So I'm interested in the multi-messenger sphere a little bit. So for those of you, who don't really care about the science that I do, let me get you a little excited, which is that essentially since 2015, we've had this ability to look at the universe in one or more different type of messenger. Classically, we use electromagnetic waves, but we can often also combine them with now more that newer and better source. No, not better. Shouldn't say that. Newer sources like gravitational waves and neutrinos, and these are usually probing very energetic phenomenon, and we want to study them. And because of this sort of like intersection, because of this intersection, we have new opportunities available. So let me walk you through sort of what the challenges could be and why you may want to use reinforcement learning in our situation. So let's say, for example, we have a merger somewhere in the universe that's taking place, and we receive signals from that binary coalescence. So these are compact objects that are merging and are multi-messenger sources because they will emit gravitational waves and electromagnetic waves, and we detect them pretty much around the same time. We have very good infrastructure at the moment that will be able to broadcast information about this merger very rapidly. Not in the matter of seconds, but pretty in the matter of minutes. You will get information via GCNs that include information about broadly what the event was like, when it took place, what the broad sky region was, where the event took place, what distance did the signal, what distance the signal was associated with. And at this point, you get surveys that are studying the skies. So, obviously we are in the LSST summer school. So Rubin is the flagship new community survey that's coming out. But there are pretty many surveys that are operational even right now that will be interested in looking at the region of the sky that will overlap with the gravitational wave. And what they could do is that at that point, they can spend a little more time studying the particular sky localization region a little more carefully. So if you can see this well, so this is, for example, the sky localization region. You could spend time getting more data in little boxes like that. Okay, you can sample it more. And again, within a matter of minutes, you get data reduced quite fast. And you get a list of a whole bunch of transients that are coincident with that region. And you can apply some initial machine learning algorithms to do real bogus classifications. You can reject long-lived sources. So, if a source has been there for a while, you probably are not going to be a gravitational wave source because that's expected to be a new transient. And you may want to make cuts on how fast the source is evolving. You want a rapid source in a rapidly declining reddish source. You expect that from theoretical models, and you may want to focus on that. And you end up with a still longish list of candidates, about 50 or so candidates, that within the time scale of seconds to minutes are then passed on to human observers who will then ponder and think about these. I'm sorry, my bunny came and is bothering me. Oh my gosh. So we'll start thinking about the list of candidates that we have and start trying to think about collecting more data to isolate which the true event is. So the thing to note here, I think, is that, all of these steps kind of happen very fast. So here is a minutes to hours time scale. This is minutes. This is seconds to minutes, so on and so forth. And at this point, you're actually spending quite a lot of time thinking about what more data would be useful. And if you are lucky, you may end up with a situation like this, where essentially, so this is a fast transient. This is not a gravitational, this is not a kilonova, which is a transient associated with a gravitational wave merger. But it's a fast transient, but you can see how fast that is. That's about, 3 days or so. And you can see how rapidly that declines. So, and there's not many data points in here, right? And this process took about a week or so for it to happen. So clearly, as you can, I'm probably asking a leading question here, but the point is that, many of these portions are actually working quite seamlessly at the moment, but there's still this issue that you have a whole bunch of candidates that are coming through for which we need to get more information to try to isolate what's going on, get probably a half decent light curve to do your inference from it. So this portion of the discovery infrastructure is at the moment pretty limited in terms of stuff that has been done to automate and make things better. So if you were to focus on that portion a little more, what happens is, as I said, about 50 or so candidates for a given merger will arrive, and networks of early career professionals, these could be postdocs and graduate students, will examine situations like the following. So these are just like, say, for example, this is light curve 1, this is light curve 2. And you can, so what you can see here is that you have no detections, no detection, no detection, no detection, and you get something, right? And it's a pretty similar situation for event 2. And then you also probably get like a little bit of a cutout, an image cutout here, which where you see a little bit of a source over here. And that source is not there in the reference image, so we get the cutout itself. And the idea is that at the initial phases, a lot of these transients look very similar to each other, so it's very hard to tell what the real candidate is. So this can be thought of as a classification problem. You can probably write a real-time classifier, but these can be limited, and I'll show you why in a second. But really the idea is that you have limited resources to get more information. So this could be data that you get from other telescopes. You can acquire more photometry, spectroscopy, and you want to basically identify which the true event is. Note that the true event is actually is very statistically unlikely to exist. So if you have about 50 events, you have less than 0.05 probability of randomly selecting the true event, and it's less than 0.05 because it's possible none of the events are actually the true kilonova, because the true kilonova is very faint. But at the same time, you want to, in addition to this classification problem, you may be interested to make sure that if you're going to spend expensive, hard-earned, with blood, sweat, and tears, resources that you've acquired on telescopes, that they be useful for other goals. So you may want to actually take the resulting light curve and have that be useful for constraining some type of physics. So this idea of actually collecting some data that is useful for some physics knowledge is not something that is done right now, because this is intrinsically hard, and this is where reinforcement learning really shines, which can tell you how exactly a particular data point will be useful for physics knowledge. So just to highlight that, since 2017, since the first discovery of the of GW17, the counterpart of GW170817, there has been no confirmed identifications of kilonovae associated with gravitational waves. So all of the processes that I was showing to you in the previous slide have not been successful at identifying the true kilonova. So it is pretty clear that additional follow-up time with the resources, given the survey capabilities that we have, is going to be critical. Because if this was the case, we could have gone and done hindsight analysis and have found the event, but we have not. And people have tried using real-time classifiers to try to make a prioritized list of most likely candidates. But what these classifiers won't, to first order, tell you is what to do. So even if you get a situation where you have some likelihoods and you get like a ranked list of candidates with like some probabilities, it doesn't tell you how to use your resources best. So essentially, there has to be a process in here that can make real-time decisions on allocating resources such that you are free from fatigue and bias. Please recall that many of these mergers can happen at odd hours, and it requires a lot of effort from people to sit and work through this list and make decisions and trigger telescopes. We also want to make sure this happens at low latency and in a scalable fashion. And the low latency, excuse me, I didn't want to advance the slide. Let's try to go back. And the low latency and scalability is important because with the improvement of detectors on the gravitational wave side, we expect to get many, to at least, depending on the statistics you want to believe, we can get at least 2 times to about 10 times more individual triggers. So going back to this setting, each individual trigger, the trigger volume will anywhere between double to increase by 10-fold. So we want to make sure that this process that we're using whatever process we're using can respond to the increased volume of data. And of course, Rubin will come in and start looking at such depths that we start getting many more transients like these at very, very faint depths. And it becomes very, very challenging to even acquire enough telescope resources to get at the depths that we will probably be seeing. So essentially, I've just said a bunch of leading stuff here that, we want to make sure that, whenever we make resources, we do this well. We've talked about a little bit here talking about bandits, but every time you think about reinforcement learning, you may often hear it in terms of games, being played in terms of games. So Adam, right at the beginning, was mentioning how this was very successful in playing Go, which is a very hard computational problem. It's an EXP in terms of computational complexity, and it had done really well against an experienced human player and beat them. And I think this was in 2017 as well, actually. Could be wrong, but I should check that. So we talk about most of this in terms of games. So I'm going to keep that because games are interesting. I think many people like games. So let's we're going to keep that language a little bit. So here's the situation, right? So you have a light curve that's happening. We want to think about what sequences of actions that you can take now and in the future. So not just things you can do now. So in the Markov decision process, in the bandit situation, we were only thinking about the one decision you take now. We weren't thinking about a batch of decisions. We weren't thinking of making a good set of decisions along the entire time scale. We were just thinking about sort of what we do best now. So we want to take a good set of decisions that are subject to probably a capped on a certain budget. We don't have all the time on a given telescope, such that you maximize a chosen objective. The caveats here is that we can only get outcomes for actions we take now. We cannot go back in time. So this is sort of like a sequential problem. You only get revealed some information, and basically the information, the complete information from you is censored. You may not know if an action that you took today was good until later. So in this case, for example, if you get follow-up photometry here, you may not do inference on light curve physics until all of the photometry arrives, but you still want to make good decisions now. And as you take a good decision, you want to make sure you adapt to that information, right? So you get something, we want to make sure that next time around we take into account what happened, so we may still make good decisions. I'm going to start formulating this in language that we've talked about a little more clearly. So we're going to talk about state action rewards, policies and stuff like that. So essentially here, like, remember how I mentioned that, we're no longer in the IID domain. We can't really use we can't really use bandits anymore because as you collect data, what you collect now is going to dictate what actions you take in the future. So let's say, for example, we have a situation where we have a light curve that's coming in. It's a very simplified situation where you have a light curve. This would be the state of your world, right? This is the collection of all the photometry that you see. Let's say, for example, the actions here that we will be considering are collecting photometry. And I'm thinking of ZTF filters, which is a project I'm associated with. And here we have two filters. We have the G and the R. We can also collect in G and R. We can take no action if we want it. And remember that any action that we take could be stochastic, which means due to various reasons, even though we trigger follow-up, we may not get it. We may not get the data for various reasons. And we now have to think about specifying a utility or a reward, or how good a particular action given a state would be. And this could be a variety of things depending on your domain. I'll make this a little more concrete as we move forward, but this is really your choice of running your model. So this could be, for example, saying, okay, if I collect some data, how much is my F1 score on my classifier going to improve? Or, for example, here we are interested, we've talked about the Q value. What is the expected improvement in the Q value, right? So, and this could be related to a physics utility, for example. We'll make this more concrete as we move forward. In this case, this is a little more complicated if you want to use the Q function, because in reality, the optimal Q value is unknown, and this is something we need to learn. And we talked about this a little bit when we were talking about bandits. And you usually start with some naive expectation and you update as you go. This is really how you learn. And then you execute some behavior policy, right? So we've talked a little bit about eGreedy, and you can actually still use eGreedy, but with a better update policy. So the eGreedy we talked about previously had no way to update the Q function. So you initially do some pooling of the arms, and then you just estimate a empirical Q value, and then you just execute a greedy policy with some random behavior. In this case, we actually, in reinforcement learning, there are mechanisms by which you can start updating this Q value. And still execute somewhat of a greedy policy, an eGreedy policy over that. Again, the details are in the weeds of reinforcement learning, which I'm not going to get into. Then at this point, once you've executed your behavior policy, for example, here you've chosen that you want to take action and you want to get data in the red filter, you just execute that and you get a certain reward. Recall in this case that actually the reward can be 0, and this is important to state that because rewards can be delayed. So say, for example, you wanted to constrain the light curve physics, you may not get the estimate on the parameters. So for example, you were interested in constraining the ejector mass, you were interested in getting for example, the ratios of the elements and so on and so forth, or a distance. You will not get estimates of any of these parameters until after the entire light curve is complete. So at a given instance, when you collect data, you may just get 0 rewards, right up until the end where you get all the uncertainties, perhaps. So this is something that needs to be accommodated reasonably. And at this point, you want to do your update. So you have executed your policy, you've received a certain return, and you want to use your learning to update your Q function or whatever behavior policy that you have. And then you keep going, basically. You keep going until you have reached the horizon, which means that the episode ends, or you have exhausted, I shouldn't have said reward, this is budget. Exhausted budget. You exhausted your budget, or you keep going, basically. If it's an infinite control type problem, I think of transients, so we usually have a fixed type horizon. Yeah. So essentially, here's how I have thought about solving this in my case. We just have 5 minutes remaining. I probably am gonna go faster through the rest of the slides. So essentially, I talked about how we're going to formulate this in terms of games. Here's what's going to happen. When a merger takes place, we get a whole bunch of information. We get a sky map. We get some probabilities that tells you, what type of merger this is. Does it have a neutron star, etc. These are standard quantities that are provided by various pipelines that are operating right now. These are classification products. And we get a bunch of light curves for a whole bunch of transients, right? We don't know which one the true kilonova here is, right? And we want to basically make sure that we are spending some resources over the next 7 days, because that's probably the maximum lifetime of the event, such that you actually maximize a certain goal that you choose. And you can choose what this is. We're going to make one choice here. There can be many events. You can have up to 500 of these choices. And so, for example, you have access to some resources. You can collect photometry via LCO, perhaps. You may end up having some low resolution spectrograph, and you can get 5 low resolution spectra, and you have to decide how you want to allocate these to the real event. And then yep. So really the question is, what is an optimal decision, and how do you make these decisions, because even if you don't have all the complete information right now. So one of the things we've talked about, explore, exploit trade-off, and how this is key in making sure that we make good decisions, and why just using a simple classifier is not sufficient. Because one of the things you can probably imagine doing is doing a ranked list. So you end up like having a bunch of probabilities that you rank the events by. But this doesn't really tell you how to actually make sure how to allocate these resources. Do you want to make sure you want to allocate the entire budget to the most confident kilonova? but that way you're not really exploring any of the other events. Do you want to make sure that you sample everything to some extent, right? Sort of spread out your budget. And we've all seen, like, examples. I think it's much more concrete now that we've gone through the specific greedy examples, that many of these naive strategies don't really work well, and they can work really catastrophically awful, especially in the presence of non-IID related data, in which case, in which setting, if you take some action now, your future actions will start depending on the data you have acquired so far. So you've gotten more information about that particular event and you want to respond to that. And another reasons why decisions can be hard is because you can make a bad decision now. So you can say, oh, you know what, I'm going to allocate everything here, but this is probably a bad decision, and you don't know that until a delay is occurred. So probably it was best to actually start pooling your bet and getting more information for other events to improve. And the ideal strategy that you will use will make sure that all future allocations and the ideal strategy is optimal given all future actions and outcomes that you may see. So essentially, this is where reinforcement learning matters, because you are able to sort of go down this sort of decision tree where you could be at a particular state. You could be at a particular state X, and you can take a particular action, and that takes you to a different sort of like part of the parameter space from which a different set of states and actions are then available. And you want to make sure that no matter which tree path that you have taken, considering all the possible tree paths, the tree path that you are choosing is always optimal, even though you never see all of it. So this should always be optimal, even though you only get to make a decision here. I'm here, but I want to make sure that I'm on this path all the time, and I never go down this path because I know that's not optimal, and that's hard to do. So we can do that in reinforcement learning. So essentially, we did this sort of a situation. It's getting closer to 10:45. So I'm sorry. Rather than zipping through, I think it's always annoying when people zip through. So I'm just going to show you the result. That's what I'm going to do. So what we had is we trained a reinforcement learning agent, and we demonstrated that compared to a random strategy, the agent was actually learning a good behavior. So essentially, as it was experiencing more and more episodes, its score was improving. And we made a comparison against human agents. And we saw basically, like, this is a very simple type of a learning agent called a linear VFA. It was very simple, but we still did reasonably well. And there's an expectation, a very clear expectation, that the moment we switch to a deep Q network, which is a neural network based Q learning, again, these are all Q functions, right? We've talked about Q functions before. The moment we switch to a deep Q network, we should do better. We did better, just a bunch of examinations. We're not going to go through that. I'm sorry, I hate zipping through slides, but as long as we get some sense, I think it's still better than rambling. Happy to talk about it offline. So sorry I couldn't be there today. I do want to stop on time so that people have an opportunity to take a breather. This can be a lot, so I appreciate your patience with me through this.
Are there any questions? Not seeing any hands in the room. Obviously, if you have questions, you can ask Ari in the Slack, or put something in the, well, I think in the Slack would be a good place. So we're going to take a 15-minute break and come back at 11 and hopefully have